So this is a different kind of problem because we've never had to try to take a derivative of two variables multiplied together. Think about any kind of derivative we've done. We do x cubed plus 3x squared plus 7x. I can say that's f of x. Okay, never two variables multiplied together, right? We've done f of x equals sine of x squared. This required us to do a chain rule because there's a function inside a function, but we don't have two functions multiplied. But the problem is here, not the problem, but the difference here is that we have x times y, right? We're doing x multiplied by y. Let's get rid of this bullet point because it's confusing. Okay, so we have a product of two variables, and we're trying to find dy dx. So this is going to introduce a new rule for derivatives, the product rule. So the idea behind the product rule is what we're going to do is we're going to take the derivative with respect to x, and we're doing d dx of this whole thing. Okay, we're going to take the derivative of the first piece multiplied by the second piece left alone. So the derivative of x is 1 multiplied by the second function y left alone. Okay, that's the first part of the product rule. Plus, now we're going to leave the first piece alone, and we're going to multiply by the derivative of the second piece. And we know that the derivative of y with respect to x is just going to be rewritten as dy dx. And then the derivative of 1, which we still have to do, is still equal to 0. Okay? So just like always, we're still going to isolate dy dx. So we get x times dy dx equals negative y, because I just subtracted that y over, and then dy dx equals negative y over x. So that's my final dy dx. Let's look at this again. All the steps for finding dy dx. Okay, and here's the product rule written out. We have the derivative, and this is something you should write down. The derivative of the first piece multiplied by the second piece left alone, plus leave the first piece alone and multiply by the derivative of the second piece, and then isolate for dy dx as always in this example. So let's color code this. The derivative of the first piece multiplied by the second piece left alone is just going to be this piece right here, because that's the derivative of x is 1 multiplied by y. Okay, and then we're going to leave the first piece alone, and we're going to multiply by the derivative of the second piece. So we're going to leave x alone, and we're going to multiply by the derivative of y with respect to x. Okay, that is our product rule. And then from here, we're just going to isolate for dy dx as always. Okay, so these steps right here are just the steps where we're isolating for dy dx, just like we always have when we've implicitly differentiated. So if you need to pause to get this down, that's okay. And then we'll move on to some more examples. So this is a curve x squared plus 4y squared plus 2xy equals 12. We're going to find dy dx, and then we're going to determine where there would be a slope of 0. Okay, so what is the derivative of x squared? 2x. What's the derivative of 4y squared? It's going to be 8 times y times dy dx plus, okay, here's where our product rule comes in because we have 2x times y. So we're going to do the derivative of 2x, which is just 2, multiplied by the second piece left alone, plus, now we're going to leave the first piece 2x alone, and we're going to multiply by the derivative of y with respect to x, which is just dy dx, and then that's going to be equal to 0. So this piece is the product rule piece of this. This is the derivative of 2xy. Okay, these two are, this is the derivative of x squared, and that's the derivative of 4y squared. So we're still going to try to isolate for dy dx, but you notice that there's a dy dx right here, and there's a dy dx right here. So how do we isolate? Well, let's first just get rid of anything that doesn't have dy dx attached to it. So we can say we have 8y dy dx plus 2x dy dx equals, we're going to subtract 2x to the, sorry, it randomly cut off recording there, but we're subtracting 2x to the other side, so now we have a minus 2x. and then we are going to subtract our 2y to the other side as well. So we have a minus 2y. And now we need to isolate dy dx, but both of these pieces have 1, so we can factor it out. We can say dy dx times 8y plus 2x equals negative 2x minus 2y. And then now we can just divide that whole 8y plus 2x over to the other side to isolate dy dx. So then we get that dy dx is just equal to this. Negative 2x minus 2y over 8y plus 2x. So yeah, here's step 1 again. And then here is our step 2 and our step 3. And then what we can do is we can actually factor out a negative 2 because it was negative 2x minus 2y. And then we can factor out a 2 from the bottom as well. Then when we do that, the 2's can cancel. So we're just left with negative x plus y over 4y plus x. Just makes it a little bit easier to interpret. So what will make this derivative have a slope of 0? We're not going to answer this full part B, where it says find all the points of the curve where the tangent lines have a slope of 0. But we can determine conditions that will create a slope of 0. So we know that if the numerator is 0, the whole slope is 0. So when is the numerator going to be 0? It's going to be 0 whenever y equals negative x. So if we think of the slope field of this, if we were to find out what this, if we type this in as a slope field, we would see that whenever y equals negative x, we would have a flat line. So if we were to draw a slope field of this, okay, well, what about at x equals 1, y equals negative 1? Okay, that would have a flat slope. What about at x equals 2, y equals negative 2? We would have a flat slope. What about at x equals negative 1, y equals 1? We would have this flat slope. Okay. Also at 0, 0, because 0 equals negative 0. Okay, what about at x equals 2, y equals negative 2? Okay, that would be a flat slope as well. So if we were to generate this whole slope field, we would see up this diagonal line all these flat slopes because that's where x is equal to, or y equals negative x. And then if we wanted to fill in the rest of the slope field, we would just plug in different x and y values and determine the slope at those points and draw a slit that models that slope. So let's think more about this. What is this telling us? Under which conditions will this curve that is modeled by this dy dx have a positive slope? What about a negative slope? Okay, so let's think of the possibilities for getting a positive when we're dividing numbers. Okay, a positive equals a positive divided by a positive. A positive also equals a negative divided by a negative, right? And then a negative equals a positive divided by a negative, or a negative divided by a positive. So let's first handle the positive case. When are both of these positive? Okay, well, x plus 7 is positive when x is greater than or equal to negative 7, right? Because if x is equal to negative, or so we should just say greater than negative 7, because when x equals negative 7, then we have this is equal to 0, right? But if x is greater than negative 7, like for example, if x is negative 6, we have negative 6 plus 7 equals positive 1. And whenever x is greater than negative 7, then x plus 7 is going to be positive, okay? What about 2y plus 4? When is it going to be positive? Okay, well, 2y plus 4 is positive when y is greater than negative 2. Because if y were equal to negative 2, then we would have 2 times negative 2 plus 4, which equals 0. So as long as y is bigger than negative 2, we're also going to have a positive number. So under which conditions will this slope be positive? Well, one condition is when, so we'll do a positive, is when x is greater than negative 7 and y is greater than negative 2. Okay. So that's what's going to give us the positive divided by the positive. Now we we also have the case where we have a negative divided by a negative, right? So when is x plus 7 going to be negative? Well, it's just the exact opposite of what we have up here. Because when x is greater than negative 7, then the numerator is positive. So what if we have x being less than negative 7, and then y being less than negative 2? Okay. For example, we could try to plug in x equals negative 8 and y equals negative 3. We would get negative 8 plus 7 over negative 2 times negative 3 plus 4. And what is that going to be? It's going to be negative 1 over negative 2, which is positive 1/2, right? So this is another possibility for generating a positive slope when x is less than negative 7 and y is less than negative 2. Okay, so now let's consider what's going to produce a negative slope. Well, we need a positive divided by a negative or a negative divided by a positive. So we already know that when x is greater than negative 7, the numerator is positive, and we know that when y is less than negative 2, the denominator is negative, so this is going to be a case for a negative slope. Or if we have x is less than negative 7, we know that that makes the numerator negative, and if we have y is greater than negative 2, we know that that makes the numerator or the denominator positive. So then this case, again, we have opposite signs on the numerator and denominator, which is again going to produce a negative slope. So these are our two cases that are going to produce a negative slope, and these are our two cases that are going to produce a positive slope. In general, when we have a fraction like this, we just want to think what's going to overall make this fraction either positive or negative. That's going to tell us when is the slope positive, when is the slope negative. To close out here, we're going to do a couple more hard examples as a closure, so you can try to do these by yourself, and then if you're feeling frustrated or feel like you need guidance, then I will do out the steps, so you can just unpause when you're ready to watch me work this out. So notice that we have a couple product rules here. We have x times y cubed and we have x cubed times y. So, product rule, we have to do the derivative of the first function, which is just 1, times, leave the second function alone, okay, plus the first function, x, multiplied by the derivative of the second function. What's the derivative of y cubed? Well, it's 3y squared times dy dx. Okay, minus. All right, what is the derivative of x cubed times y? Well, it's going to be 3x squared, the derivative of the first piece, times the second piece, okay, plus we're going to leave the first piece alone, so we're going to leave negative x cubed alone, and then multiply by the derivative of y with respect to x, that's the second piece, and then now that is equal to 0. Erasing that second example for a second just because it was in the way. So now, this is a crazy long expression, but we have to end up ultimately isolating dy dx. So anything that does not have a dy dx attached to it needs to get moved to the other side. So now we have x times 3y squared times dy dx, okay, minus x cubed dy dx. Those are our two pieces that have a dy dx, and that's equal to, we're going to subtract that y cubed over, so we get minus y cubed, and then we're going to add the 3x squared times y, so we get plus 3x squared times y. Okay, we need to isolate out that dy dx, so that's going to give us factor it out. Dy dx equals x times 3y squared minus x cubed. Okay, we just took out that dy dx from both of those pieces, right? And that's going to be equal to this side of the equation. So now we just need to divide by the x times 3y squared on both sides. So we're going to divide by x times 3y squared minus x cubed. Okay, so then that leaves us with just dy dx, so dy dx is equal to this. So if we just follow our product rule and then do the other basic derivatives and then get dy dx by itself, that's all we have to do to ultimately isolate and find our slope. So this looks complicated, but this is a complicated curve, and these whatever x and y value we want to plug in, it'll tell us the slope of this complicated curve at any given time, or at any given point. All right, this last one's a little bit easier. We have x squared plus 2x plus y to the fourth plus 4y equals 5. Okay, but this, I just realized that first one asks us to find the slope of the curve at x equals 1. And we're just not going to do that. We found dy dx and that's enough. But we will find places where there's a horizontal tangent line in this second curve. So first we have to find dy dx. So we get 2x plus 2 plus 4y cubed dy dx plus 4 dy dx, and that's equal to 0. So again, we need to get everything without a dy dx to the other side. So we get 4y cubed dy dx plus 4 dy dx, and that's going to be equal to negative 2x minus 2, because we're going to subtract those pieces over. Factor out a dy dx. 4y cubed plus 4, that's equal to negative 2x minus 2. Okay, now we just have to divide by 4y cubed plus 4 on both sides. Okay, so then this is our final dy dx that we just found, because these are going to cancel, leaving us just dy dx. So it does say to find the coordinate point, meaning an x and a y value, but we're just going to go ahead and just do the x for now, just because that's a more complicated topic that I'd prefer to not cover in this kind of setting. So for now, we'll just determine the x value that makes this a horizontal slope. So what's a horizontal slope? It's when the numerator is 0. So we just have to set negative 2x minus 2 equal to 0. So negative 2x equals 2. So then x equals negative 1. So at x equals negative 1, this curve is going to have a horizontal slope because it causes our dy dx to be equal to 0.